This is week 3 for Mentech 3MF3. Today's agenda, we're going to conclude our strain rate effect. Then we will talk about how to determine the empirical material constant. Then we will go into material consideration in design. And whenever we process any material, we have to look at the crystal structure. So I'm going to talk about a crystal structure of steel. Then we're going to see how the chemical composition can somehow give you a hint on how to process the material, okay? Then we're going to, if time permits, I'm going to go into case study number 1, an actual case that I've implemented a solution in industry, okay? So we are talking about Uzbor 1500. Thing to take note, assignment number 1 will be posted on September 22nd, okay? And you are going to hand in on Avenue to Learn. Some student asked me, how do I assess the recorded content? Okay, so to assess the recorded content, you go to the announcement. Okay, so I'm going to view this as a student, okay, because I don't know what you see. So as a student, you see this, right? And you go to welcome. At the welcome, you can click to the link to the lecture. Okay, so I'm not going to provide you the link every week. Okay, you just click onto this. Oh, it did not work. It's okay. You just copy the link. Okay, and then you go over here and you just press enter. Okay, so this is our lecture, Mentech 3MF3. So week 1, so this is week 2, week 1, I did not do any recording. And you just click on them and you watch. These are all the recorded videos, okay? If there's anything that you miss out, okay, during the lecture, you can go them. So I partition after class, okay, I partition each of them into 15-minute segments, okay, some less because towards the end, and then you watch them. Are we clear? Okay, or there's anything that, hey, I'm not getting this, you can go back and have a look at this. I was being asked what extra books that you can read, okay, regarding the content that I'm teaching. So you can go into the book Digamos. Let me go into Digamos that we have, okay. I'm not going to tell you how did we get those books. So you have a textbook as Digamo. So last week, what I taught was deformation, plastic deformation. So in order to look at a book like that, it's a lot of content. You just go to the last page and look at deformation. Okay, so you go to the end of the book, you look for keyword. Okay, and the keyword is deformation. Okay, so you look, is there any deformation? DEF. So there's no deformation. How about plastic deformation? Okay, so you're going to look at P, look at plastic, PL, ASTIC. Can you see this? Plastic deformation, okay? So page 63, 96, 379, okay, you read these chapters. Are we clear? Or these pages, okay? So this is how to go. Because what I'm teaching you is based on different parts of the books, okay? Not on what? On chapter. Are we clear? Okay, so it's integration of knowledge. It's like manufacturing. Right. So today, we are going to continue our strain rate effect. So we did mention the strain rate effect, all right? If you look at this equation over here, we have more or less look at strain hardening. And then the next term we had is our thermal softening. Just to quickly recap. So when I write out all this equation, you more or less have a good feel of how they behave. And then we finally have the strain rate effect, right? So just quickly recap. This is what strain hardening. And if you look at the units, these units is in what? Pascal. Okay, if we were to look at the units. And over here is thermal softening. And for this case, we know theta divided by theta, it become unitless. And the last one, this is what we call strain rate effect. Again, this is unitless. And we know the thermal softening factor will always be less than 1 because this is minus, and this will always be greater than 1 because this is what? Plus. Are we clear? Okay. So from here, we can see based on thermal softening we spoke about last week, the value C, right? The C value, or the higher the C value, it indicates that the material is more strain rate sensitive. Okay, just to recap. So strain rate sensitive, what does it mean? It means sensitive to deformation speed. Okay, deformation to what? Deformation speed. The higher the C value means it's more sensitive to deformation speed. The lower the C value means it's not sensitive to deformation speed. I'll give you an example. So we have a material known as AISI 1045. And the C value we have is what? We wrote this last week. I can't remember now. The C value is 0.022. Okay. And in general, if we were to look at if we go in and look at a aluminum alloy, okay, this is equal to 0.0001. Okay, very small. Okay. Now let's look around of you over here. How many of you are working in a company doing deformation of aluminum? 1, 2, 3. That's quite a lot. Yeah, I'm surprised. Donald Trump effect. No China, no Mexico, except come to Canada. So what can you all tell me about deforming aluminum? Anyone? Hey? Yep, easy to deform. How about in terms of strain rate? Those of you who are working in places where you deform aluminum, any idea? Is it very easy to deform, or strain rate means nothing? What is it? Yeah, you can easily bend. But how about the speed of deformation? No, we have not done a lot of deformation. Not to worry, because not everyone is in deformation error. So if you see a value of C like this, okay, and if I have a scale over here, okay, so this is deformation speed. Okay, so this is we are going to start with AISI 1045. Then we have our aluminum alloy. Okay. Someone said something. Are we okay?
Yeah, I can hear.
Are you okay online?
Yes, yes.
Oh, you're okay. Yes, yes. Okay. So you have over here deformation speed. Over here is what type of material. Okay. So you have 100, 200, 300. So this is deformation speed. It's in meters per minute. 400, 500, 600, 700, 800, 900, 1,000. Okay. For 1045, okay, your deformation speed is between 200 to 300 meters per minute. Okay. And this is also due to its use strength. Okay. So at this range, it's also dependent on use strength. Okay. So 1045 has higher use strength for aluminum. For aluminum alloy, so when I draw the box down there, that is your deformation speed. You can deform this very easily, okay, with ease between 200 to 300 meters per minute. For aluminum, you look at the C value is very what? Oh, okay. And the use strength for aluminum is usually lower than what? Than steel. So when we deform aluminum, we can start from where? 600, okay? And we can go up to 'any idea? That's why I'm surprised some of you still work in companies that produce aluminum, which is pretty impressive. Okay. So what does this mean? I'm just clowning around down here, okay? This means when processing aluminum, you can go up to what? 7,000 meters per minute. Okay. You can deform at that speed. Basically, if you were to deform aluminum, is how fast your machine can go. You see that, right? Whereas when you deform steel, okay, my machine can deform up to 1,000 kilometers per minute. We only can use what? 200 to 300. Whereas for aluminum, generally what we ask is how fast this thing can go, right? How fast your machine can go. Okay, I process aluminum at 7,000 meters per minute before. Okay, and that's not the quickest. Companies like Boeing When they machine aluminum, they machine at twice the speed of sound. So what does this mean? Okay. Manufacturing aluminum, you don't need knowledge.